Hello, this is Jason Kendall, and welcome to the next in my Cosmology series. If you're just tuning in, please go and look at my playlist on my YouTube channel about the Cosmology series, so you can start at the very beginning. We're into Chapter 2 and Section 2. This is about the fundamental observations of the cosmos, and we're talking about homogeneity and isotropy. So what exactly is homogeneity and isotropy? Let's look at some examples. Let's say you're in a big forest and you look in any direction. No matter which direction you look, you're going to see a tree. And so from a directional perspective on the floor of the forest, it's isotropic with respect to trees. So some trees are closer, of course, closer than others, and so they look bigger, but every tree, no matter what, in every direction, you're going to see a tree. Also, if the forest is really big, it doesn't matter where you're looking from inside the forest. You're just going to see a bunch of trees around you. And in fact, everywhere you go, you're going to see trees that look bigger because they're closer to you, and they won't be really small if you go over there simply because they look small to your eye here. No, they will be roughly the same size and roughly the same place. However, we notice that if we look up, this violates it, and if we look down, it violates it. So we're looking mostly straight through the forest to see exactly what we mean. Therefore, homogeneity and isotropy are not the same thing, and they don't imply each other. One is where we stand, and the other is where we look. Where we look is isotropy. When we look out into a particular direction and see the same thing in any direction, that is isotropy. And that's what we can think about as the center of this bullseye here. So if you're standing at the center and looking in any direction, you're going to see the same thing in every direction. However, that's not homogeneous. If you weren't at the center, you could tell which direction is preferred simply because, well, you can see a different arc of things, and maybe you'll see a line of purple and blue, and the radius of curvature of the lines will change as you get farther and farther away. So it's not isotropic, but it's isotropic around one point, and it is not isotropic anywhere else. The lines that we see on the right, those lines are homogeneous, but they're not isotropic, meaning no matter where you go, let's say this is an infinite set of lines, and just in the same way the bullseye we can think is infinite, but if it's an infinite set of lines, then no matter where you drop, you're always going to see the same structure of lines. But there's a preferred direction of up and down, so that violates isotropy. It'll be homogeneous, meaning it's roughly the same stuff wherever you stand, but it doesn't look the same in every direction. So therefore, isotropy is about which direction we're looking, and homogeneity is what's it like right around us where we're standing. Isotropy itself, cosmologically, because that's what we really care about now, is the isotropy and homogeneity of the cosmos. Isotropy only works on the largest size scales. So what does that mean? Okay, so let's take a view then try to find directional things of what we mean by isotropy in the universe. When you look at the Earth-Moon system, which is about 200,000 miles across, there's a preferred direction from the Earth towards the Moon. So that is definitively not isotropic. And if we scale it out a bit bigger to a couple of astronomical units, it's still not isotropic because the sun provides a preferred direction. And if you don't know what that means, just look up on a sunny day and you see the sun. There's your preferred direction towards the sun. And if we went out to about 50 or so astronomical units, included most of the outer solar system, it's still not isotropic because there's still the sun, and there's a disk-like shape, which is the plane of the solar system. That's not isotropic because up and down are different than side to side. Now, if we look at the scattering of nearby stars within a few parsecs or so, it looks kind of isotropic-ish on a few parsecs out to the nearest stars, but we can make out a preferred direction out of that big thing off to this direction about 10,000 light years away, the center of the Milky Way. And the Milky Way itself is not isotropic because it's a disk shape and there is a center. So in our perspective of, yeah, if you were at the center of the Milky Way, it might look isotropic in the same sense as that target, but up and down out of the plane of the Milky Way is certainly not isotropic. And this is on size scales of about 100,000 light years. So let's go bigger. If we then go out to a few megaparsecs, about 3 or so megaparsecs, we are including the local group of galaxies. That would be the Andromeda Galaxy, Milky Way, the Triangulum, and others. But this is still not isotropic because we can make a preferred direction the line between the Milky Way and Andromeda, and that still gets us a non-preferred direction. So let's get even bigger scales. Our local Laniakea supercluster encompasses about 100,000 galaxies stretched over 160 megaparsecs, or almost 500 million light years. It's about 100,000 times the mass of our galaxy, and it has about 4 separate subclusters that once were called separate superclusters. But we can still define a center of mass to this supercluster and then show some sort of orientation. Let's get bigger. Now, if we look at the size scales of greater than about 200 megaparsecs, or greater than 500 million light years, we don't find any extra large grade A super duper plus size superclusters. So the biggest superclusters are about 200 megaparsecs in size. That means we're now discovering roughly the scale of the isotropy of the cosmos. And if we get out to look at the observable universe, we see that it's about 30 gigaparsecs across from the one side of the observable universe to the other, is about 30 gigaparsecs. And it's certainly isotropic around the center of the diagram, and it also seems to be hinting about isotropy elsewhere inside of there, meaning it doesn't seem to be a preferred place. So we definitely are seeing isotropy on the largest size scales of 200 or so megaparsecs out to the observable universe. What we were looking at before was just simply a diagram. So where does this kind of information come from? Well, it comes from things like the 2DF Galaxy Redshift Survey, which shows the distances and positions of galaxies in the cosmos out to a limiting magnitude or limiting redshift and therefore a limiting distance. So the surveys themselves tend to be kind of pencil beam and narrow. So if you were to look at them, they kind of look like pizza wedges because we're looking at a narrow band of sky, but scanning across. So it allows us to see what these galaxies are in a given direction. Now, if you look at this survey, we see that from the center, the vertex, where we are looking outwards, we see that roughly the same things are in roughly every direction, no matter what, when we look out from the center of there. So the isotropy itself statistically looks from one angle, one direction to another, roughly the same on the size scales of about 500 million light years, or about 200 megaparsecs. And that's what we see. We see groups punctuated by voids, punctuated by groups, punctuated by voids. And so it's roughly the same stuff in every direction that we see. And this is true for almost every galaxy redshift survey that's been done. Well, not for almost every, it's been true for every galaxy survey that's been done, such as the Sloan Digital Sky Survey and others. Isotropy is actually best confirmed on the cosmic size scales through the cosmic microwave background. The current state of observational work has spectacularly confirmed and greatly strengthened the observational case for the Big Bang standard model of cosmology. The cosmic microwave background shows a perfect blackbody spectrum no matter the angle you're looking. It's characterized by a single temperature across the entire sky of 2.725 Kelvin, plus or minus 1,000th of a degree. It uniformly fills the universe, and the variations in the temperature that you see in this map for the Planck mission that was released in 2018 is that this is better. These differences in temperature between the red and the blue are 1 part in 100,000. And these then become the seeds for large-scale formation and galaxy structures later on in the universe's history. So this is truly the test of isotropy. The anisotropies in the universe of the cosmic microwave background are 1 part in 100,000. Now, you might think, oh, it's just the Planck mission. Well, it's not unique. This started with the observation by Penzias and Wilson. There were other ground-based observing structures, to balloon-based experiments, to space-based observatories with the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe. ESA's Planck, a number of missions and experiments conducted at the South Pole and northern Chile, they've all confirmed the isotropy of the cosmic microwave background, which reflects the isotropy of the universe as a whole. Now let's take a look at homogeneity. Homogeneity is a lot trickier to observe because homogeneity says where you're standing, right? So we can't really move 200 megaparsecs to the right or anything. So that's really hard. So let's look at it from a slightly different perspective. Consider the average density of the universe. According to the Planck data, the Planck cosmic microwave background data, the Hubble constant today is about 66.88 kilometers per second per megaparsec. And that gives the critical density, meaning the difference between an open and a closed geometry universe, and a critical density of approximately 8.4 times 10 to the minus 27th kilograms per cubic meter. That's really nothing. That's only a few protons every square meter, right? That's really not much. So the baryon density is a tiny fraction of that. It's 2% of that, which is 1.86 times 10 to the minus 28th kilograms per cubic meter. And that's one proton for every 4 cubic meters. That's what the mass is, that's what it works out to be. So that's a very, very, very low density. Let's see how that works out. Locally around U, so we're going to try to determine how good our homogeneity is by saying, are we typical of the density of the average universe? Locally, you're about, right around U is about 100 kilograms inside a cubic meter centered on U. So no, it's a pretty big compared to the average cosmic density. If we then look at the average density of the Earth as a whole, that's about 5514 kilograms per cubic meter. That's still way, way, way too large, much bigger than about 2 times 10 to the minus 28. Let's now expand the idea and look at the inner solar system and take about a couple of astronomical units out and look at mostly the mass of the sun that's inside of there. That drops the density down to about 5 times 10 to the minus 6 kilograms per cubic meter, but still that's really large. Let's get our size scale even bigger. Take the entire Milky Way, which has a mass of about 6 times 10 to the 42nd kilograms, and the volume of the Milky Way, which is a disk with a bulge in the middle, that's about 7 times 10 to the 60th cubic meters. Now we're getting close, but we're still not there. That's about 8.5 times 10 to the minus 19th kilograms per cubic meter. And still, that's a billion times too dense. Now let's grow our size scale out to the local group where it's about 1.3 times 10 to the minus 27th kilograms per cubic meter. And that's about 10 times still too big than the average density in baryons, in only baryons in normal matter. The density of the local group would of course include dark matter. So that's going to be large. I'm looking specifically at matching the baryonic homogeneity. Only on the size scales of superclusters, once we're looking at 200 megaparsecs or so, does the baryonic density drop to the cosmic average when we start to figure that in. Otherwise, the homogeneity, we don't get to that point. Why we use density is because homogeneity means even mixing. So if you mixed everything out evenly and took an average, that's another way of looking at homogeneity. So only on the size scales of superclusters of galaxies does it finally drop to that cosmic average. Now, because we're looking at homogeneity as a cosmic average of stuff, that means that if we're looking at stuff, then stuff probably behaves the same everywhere. So homogeneity has a very interesting implication. And that means that the same physical laws apply everywhere in the entire universe. And that we can actually see in the great distance that things look roughly like galaxies and expanding clouds of hydrogen gas, and we can explain things with black holes and star formation. That's actually a really good, powerful assumption that it lends credence to this idea. And so far, no observation yet has invalidated our understanding that current physics that we know locally, locally means out to a few, even megaparsecs, that we can't apply it to the rest of the universe. This leads us to the core central idea of all cosmological study, and this is the cosmological principle. We're going to first start with the Copernican principle that says that there's nothing special about our location in the universe other than the fact that this is the place where we call home and it's where we live. But if you take isotropy around any point in the universe, and we've spectacularly confirmed it with the cosmic microwave background, and you combine that with the Copernican principle that says there's nothing special about our location, then that means isotropy around one universe there's isotropy everywhere, around every point in the universe. And so isotropy everywhere means homogeneity everywhere. Therefore, combining the Copernican principle with isotropy around any one point means it's homogeneous in the universe. The cosmological principle is therefore that the universe is everywhere isotropic and homogeneous. This means that anyone, any observer, anywhere would see roughly what we see, no matter where they looked. And that's a very important point. Everybody and every observer sees exactly the same thing. Now, the cosmological principle says that everybody everywhere says everything. But there's also a concept where we can call it the perfect cosmological principle, that everybody everywhere everywhen sees the same thing. So therefore, we take the Copernican idea that not only are we in a special place, but we're not in a special time. And if we are not in a special time, that implies the steady state model of cosmology. And the steady state cosmological model has, unfortunately, even though it's a very elegant model, there's a lot of evidence against it. The cosmic microwave background was the first that put the steady state model to bed because there's nothing inside of the steady state models that can actually create a proper cosmic microwave background. Also, later, the galaxy evolution surveys, such as the Hubble Ultra Deep Field that's seen here, where as you examine this pencil beam survey of the Hubble Deep Field, you see foreground galaxies that look highly evolved and background galaxies which are tinier, redder, and much more misshapen. So there is a progression of galaxies from then to now, meaning we don't see, if the steady state was true and there was no special place in time, then if we look in the Hubble Deep Field, we should see things exactly like the Milky Way, no matter how far away we look. And we simply don't see that. So the perfect cosmological principle is false, and along with it, the steady state model. There are also some amazing philosophical implications to the Copernican principle. It asks us to permanently change our understanding and view of the specialness of humanity. Every single advancement in the understanding of science and technology, and many things in the arts and the letters, has helped make us less special in the universe. And I don't mean less special like as in we're not special because we're alive, or we're unique individuals, or that dolphins are really cool, or spiders are cool, or any of that stuff. No, we're not special because we're not unique. Once we discovered atoms, the discovery of atoms showed that everything's made up of atoms, including us. The discovery of the distances to the stars said, wait a second, that bright disk in the sky, that sun thing, that's those points of light that are way up there in the night sky. They're just like the sun, but very far away. When we discovered that humans and other primates are very similar, in fact, we have some deep similarities to even trees, that showed us that we're not really that special. More recently, we discovered exoplanets, planets around other stars, which shows that Earth and Venus and Mars and Jupiter aren't unique. There's planets everywhere. And in fact, the James Webb Space Telescope is currently available to observers who are making proposals and get it done. But it's able to see spectra of planets in the habitable zones of nearby stars. And so we might find in the next decade or so that life itself in the universe isn't special either, and that the Earth does not hold a monopoly on life. Now, I'm going to probably say that if we're going to say the nature of homogeneity, my personal bet is that there's one sentient life form that can understand, well, this particular YouTube channel within 200 megaparsecs, and you're part of it. I think that sentient life is extraordinarily unique, but if we take 200 megaparsec size scales, maybe there's one in each. That would be a good size scale. Give me a couple 100,000 galaxies and with trillions and trillions of stars and trillions upon trillions of planets, then we're starting to have the chances for life to rise into sentient nature again elsewhere in the cosmos. But life itself, finding bacteria, we're going to find that. We're going to find that probably around either on Mars or maybe in Enceladus or in Titan, but probably around some other planet sometime in the next 20 years or so. These philosophical implications of the Copernican principle just says that we're not special and we're in no special place. And that's what we mean by the isotropy and homogeneity of the cosmos. For cosmology, it means that the same physical laws apply everywhere in the universe, that every observer will see everything the same way we see it, no matter where they're located in the cosmos. Not when, today is different than ago, but no matter where you are in the universe, that's what you'll see. So the law of the universe's redshift is expansion that you'll see anywhere in the universe. The cosmic microwave background, you'll see it anywhere in the universe. Galactic evolution, you'll see that anywhere in the universe. Cosmology relies on this Copernican principle and the cosmological principle to show that the universe is homogeneous and isotropic. And in fact, we have observational evidence for those things. And thanks for watching. I just want to take a second and thank my Patreon supporters who've been fantastic for all this. They're giving me a lot of support. And if you would like to join me and get some preview content, please become a Patreon subscriber. Also, if you like this, please do hit that like button and subscribe to the channel because I'm going through the entire textbook of Barbara Ryden's cosmology book. And it's going to be a long ride. And this is the third of many videos. And we'll see you next time.